We are going to continue our study of related rates by looking at cone problems and cylinder problems. So in this example, we have a water tank in the shape of an inverted cone. The height of the cone is 10 meters, the diameter of the base is 8 meters, as shown in the diagram, and water is being pumped into the tank at a rate of 2 meters cubed per minute. How fast is the water level rising when the water is 5 meters deep? So there's lots of information given here, and the one thing you have to be careful of when doing cone questions is as the water is rising in the cone, it is also growing, the radius is also growing, and as it goes up the cone, the radius is not a constant. So there's a rate change in the height and there's a rate change in the radius. Now, let's write down what we know. First of all, we know that this is the height of the cone, so I'm going to use a subscript. The diameter of the cone is 8, so therefore the radius of the cone is 4 meters. And we know that water is pumped into the tank at a rate of 2 meters cubed per minute, so that's my change in volume with respect to time. And the question is asking how fast is the water level rising, so we're looking for dH dt. At the instant, the height of the water is 5 meters deep. So there's height of water and height of cone. You've got to keep those separate. Now, the formula, and this would be provided for you, the volume of a cone is 1/3 pi r squared h. Well, in this problem, we're trying to find dH dt, so that means we want to get this formula in terms of just variable h. So somehow I want to get rid of that r. Well, this is the only time we take our original dimensions of the cone. And we're going to set up a ratio. And we're going to say the radius of the cone divided by the height of the cone is 4/10. And if I bring the h up to the right-hand side and simplify, for this particular cone, the radius is 2h/5. So now I can use that to plug in r, and then I'll have the volume of this particular cone just in terms of h. So let's do that quickly. So volume is 1/3 pi. In place of r, it's 2h/5, and it's squared times h. So now we have to square our fraction. So this is 4h squared over 25 times h. And if I clean this up, multiplying all the numerators, I get 4 pi h cubed. And multiplying the denominators, I get 75. So now I have the volume of this particular cone just in terms of h. Now I take the derivative of both sides with respect to t. And remember, this 4 pi over 75 is just a constant. So the derivative of v with respect to v is 1. And then we multiply it by dv dt. 4 pi over 75 is a constant, so I'm taking the derivative of h cubed. So if I bring the 3 out front, that becomes 12 pi over 75 h squared times dH dt. And now it's a matter of plugging in the values that I know. I know dV dt, so this is given. I know the height of the water they want me to calculate, so I could plug in right now and then simplify. So if I do that, I would get 2 in place of dV dt. 12 pi over 75 really reduces into 4 pi over 25, just divided by 3. And they want us to calculate this when the height of the water is 5. I have to square it times dH dt. So if we quickly look at the right-hand side, 5 squared is 25, and that 25 is going to cancel. I divide by 4 pi. And that's going to equal my dH dt. And 2 divided by 4 times pi. This works out to be 0.159, and that would be meters per minute. So therefore, you'd say the height is changing at a rate of 0.159 meters per minute. Now, how do I know it's meters per minute? Because it's change in height over time, and height is one-dimensional. You could have left your units in, and they would have canceled out to become meters per minute, but in this particular case, I just plugged the numbers in and worked out the final answer. Okay, so all of our cone problems are done the exact same way. Okay, we look at what variable either I want to get rid of r or get rid of h. So I set up this ratio with the original dimensions of the cone, isolate the variable I want, plug it back into the volume of the cone, take the derivative, and solve for what you're looking for. Okay, ones similar to this are ones dealing with cylinders. Now notice in a cylinder, the difference between a cylinder and a cone is with a cylinder, as the water is rising, the radius is a constant. So the radius isn't changing as in a cone. The radius would change as the water rises because the cone gets wider and wider. So these ones are easier, okay? And this was from the 2019 actual AP exam. And it tells us the cylindrical barrel with a diameter of 2 feet contains collected rainwater. The rainwater drains out through a valve not shown on the bottom. The rate change of the height of the water in the barrel with respect to time is modeled by this equation right here. Part A is saying find the rate change of the volume of the water with respect to time when the water is 4 feet. Okay, so they give us the volume of a cylinder. So there's our volume formula. Okay, now in this case, because the radius of the cylinder is always constant, I can plug the radius in right away. So if the diameter of the cylinder is 1, I know the radius is going to be 1. So therefore, volume is going to be pi h. And now if I take the derivative of this equation with respect to time, the derivative of v would be dv dt, and the derivative of pi h would be pi times dh dt. Now in this particular case, they gave us dh dt is right here. So this is going to be pi, and dh dt is negative 1/10 root h. And in this particular problem, they wanted us to calculate it when the height of the water is 4. So dv dt is going to be pi negative 1/10 square root 4. And this would be negative 2/10, which is negative 1/5 pi. And my unit would be feet cubed. And my time is given to me in seconds. And that would be your final answer. All right, so there's 2 examples for you to look at, and that'll help you with this assignment on page 290. So if you have any questions, feel free to send me an email, and good luck with these problems.